All right, I think we're ready to get started. So good afternoon, everybody. Welcome to the latest edition of our virtual tech meetup series. It's my great pleasure today to introduce Alex Merced, who'll be talking today about memory management in Rust. Before we dive in, I just want to have a quick word from our sponsors. So today's meetup is brought to you by LogRocket. I'm sure the vast majority of you joining us today came via our blog. We also have a product for when you're building and fixing applications. LogRocket is a front-end application monitoring solution that combines error tracking, digital experience monitoring, performance monitoring, infrastructure monitoring, and web analytics, all rolled into one. So your engineering teams, product teams can all use a single source of truth to look at all of these aspects of app development, so you can have more efficient remediation of your issues and iteration of feature sets, in addition to its integration with all of your backend monitoring tools. For more information, head over to logrocket.com. You can get a personalized demo, or you can sign up with a free account and just get a taste of what the solution can do for you. Now, with all of that out of the way, I'd like to welcome Alex to give his talk. Just so you know, a recording of this will be sent to you in addition to being uploaded to our YouTube channel, where you can also watch previous editions of our meetup series. In addition, we also have some upcoming meetups that you might be interested in, including front-end developer experience on September, it's actually tomorrow, and then we have configuring Apache for Node.js next week, and then the week after we have using Playwright for end-to-end testing. If you're interested in signing up for these, you can just Google LogRocket Tech Meetups, and they'll bring you straight to the page where you can see what we've got coming up. If you have any questions during the webinar, please feel free to leave them in the chat, and I'll try and get to them at the end. Now, without further ado, take it away, Alex.
Hey, everybody. Let me just share my screen. There we go. We'll get this show on the road. Hey, everybody. Welcome to this presentation. We're talking about Rust memory management. Basically, the idea here is we're talking about what makes Rust so unique. So basically, the thing that it really does that's very different than other languages that makes it sort of like the darling of the developing world that we have today. Also, let me just introduce myself. I am Alex Merced. I am full-time. I am a developer advocate for a company called Dremio, so talking about like data lakes and data lake houses, all that. I also am an instructor over there at General Assembly Bootcamp, so I train a lot of incoming developers, and I just love creating content regarding web development, data engineering, etc. So to find out about content I'm creating, feel free to follow me on Twitter at those accounts listed below, and then you can check out my blogs over there at grok.overflow.com and many pieces that I've written for LogRocket on LogRocket's blog. Now, in today's presentation, again, we're going to be covering sort of like why Rust does what it does and why it's important. So basically, to understand like why Rust, we have to understand like why not C, why not Python, and just talk about sort of like the considerations we have with that when it comes to either things like performance or things just sort of like the ease of being able to make mistakes when it comes to things like memory management and whatnot. And then we'll go back and take a look at how Rust does it differently, and really be able to kind of like sit back and appreciate why Rust is so unique among like the vast sea of programming languages out there. Okay, particularly with like the way Rust manages memory, features like Rust borrowing, etc. So essentially, like the fundamental problem is going to be sort of on trying to figure out two problems. Like one, at the end of the day, memory has to be allocated and it has to be deallocated. Every language kind of handles this differently. So a lot of higher level languages, me, the developer, would not have to worry about that. So when I'm writing JavaScript, when I'm writing Python, when I'm writing Ruby, I don't have to generally worry about this whole allocation and deallocation process because of mechanisms we'll discuss later on. And then also there's going to be an issue where sometimes we have something in memory and we might have multiple things referring to it. Okay, so then you run into this issue where you might free up that memory, but there might be still like a variable in scope referring to that spot in memory that's now been cleared out. That can cause problems when a program is running, runtime errors, compile errors, all sorts of different types of errors that we would like to avoid. So basically, at the end of the day, it's like we just want to make sure that we can write a program that I'm not going to have any memory issues. Okay, I'm going to make sure that I can free up the memory I need to free up, so that way my program can run fast. Okay, but I also want to avoid the issues of just accidentally referring to non-existent things that'll just completely shut out my program and ruin my user's experience. Okay, so And at one end we have C, and this same rules pretty much go for C++, where basically memory is pretty much explicitly allocated. When we say explicitly allocated, I mean specifically when we talk about memory on the heap. So again, memory in a computer could be coming from two places. There's like the stack, which that's just going to kind of manage itself. Every time you run a function on a computer, all the memory that function uses up is going to be on the stack, and then once that function is done, it's just going to clean itself up. But sometimes I'm going to need things that exist between functions. So it might get created in this function, but I'm going to need it after this function is done. Okay, so we need to have this place that's like, that memory doesn't just automatically get cleaned up, and that's the heap. I always just kind of imagine like a stack as like the stack of pancakes. We eat the pancake on top and it just kind of naturally cleans itself up. And I imagine the heap like a heap of potatoes. There's no like obvious start or beginning. It's just a heap of stuff. So essentially here, like in this code snippet you see here on the screen, I'm going to allocate some memory using malloc. I'm going to allocate memory that's big enough for an array of 10 integers. Okay, and then later on, once I'm done with that memory, once I'm done with that array of 10 integers, I'm going to be like, well, I don't want to use up this memory because I'm going to need it for other things. Okay, because the less memory I have, the less things I'll be able to do later on in the program. So I'm going to then free up that memory. So I'll pass the array to the free function. Okay, but again, the problem comes in is like, what happens if I have other variables referring to that memory? Okay, because I can create multiple pointers pointing to that memory. Okay, and also understanding when we create those additional variables. So let's say we're talking, and then here we're generally talking about complex types. So we're talking about like in C and Rust, we generally use structs. So structs are a little bit different than objects if you're using like C++, Python, JavaScript. Usually with objects, you create like a class, and then with a class, you can then instantiate an object. So I can describe what a duck is and then create ducks. It's generally the same principle with a struct, except the struct doesn't have methods. So a struct is just the properties, so like a name, age, and that's it, while a class is properties and methods. And so based just little distinction between sort of like C and Rust, which generally have structs, versus C++, Python, whatnot, generally which have classes that can instantiate objects. But either way, these are complex types. And what happens if I say A equals a new duck? So I say A equals a whole new duck object, and then I create another variable D and I say it's equal to A. How does C treat that? It depends on the language you're using. In C, what's going to happen is actually going to make a copy. So if I had a duck object or a duck struct, and I do B equals A, what's going to happen is I'm just going to have two identical copies of that struct. They're each referring to a whole different duck, even though they're the exact same a copy of the exact same duck. So the properties are the same. That's fine. So now I have two. I'm basically using double the memory. That's fine. Which maybe I don't want to do. Okay, so maybe what I want is to use that same duck. Okay, so in that case, in a language like C, the way you would say, okay, I want two variables to point to the same duck is you would use pointers. Okay, so here on the code snippet to the left, this is going to be where we make a copy of the duck. So you see here, in this case, we're making a number struct. So we define a struct called number, which just has one property, the num. So we then create two variables, A and B, that both hold a number. And I'm going to say, okay, the A has a property for the num property that equals 1. And then I'm going to say, hey, B is going to equal A. Okay, so again, this is C, so it's going to end up making a copy. So now I have two copies of this number object. So now when I change B's num property to 6, what's going to end up happening is that when I print out both values, A is going to print out 1, B is going to print out 6. Okay, and the reason why that matters is because the reason why they're going to print out different things is because they are two distinct objects, even though I copied it at some point. Okay, but what if I don't want to have to copy it? I can again use a pointer. So in the code snippet to the right, it's basically the same example, but notice B I declare as a pointer. So that's what that asterisk means. I'm declaring that this is not just a number object, it's a pointer pointing to an already existing number object somewhere in memory. So I basically go through the same sort of process where basically I say, hey, A's num property equals 1. But now I'm saying B doesn't equal A. And so I'm saying B equals the reference to A. And then I can now access the num property through B of A, which just means basically they're both pointing to the same object, that same number object. That's fine. That works. That's great. So again, I can do both ways. The problem is, as you start making all these variables, you may forget to clean up some of these variables, or you may use some of these variables after you go up and you free up that memory. And this creates like null pointer references where you have a pointer that's pointing something to something that doesn't exist, which may not be caught when you're compiling. So it's not necessarily an error that you'll catch during compilation time. So in that case, what's going to happen is you issue software with runtime errors, and someone's using the program and it just crashes on them, and they're like, well, wait, why did the program crash on me? And no one wants to kind of issue, you don't want to release software with that kind of like user experience. It's the kind of user experience that even if you fix it, might sour them on using it further. Okay, so they generally, we want to always have kind of systems in place to kind of try to prevent these types of problems. Okay, so we'll see, you got to be really careful for those things. Okay, but then one approach is to kind of have that whole process automated. And that's when we get to higher level languages like Python, JavaScript, Ruby. Here you'll have just basically this ongoing process that just figures out, hey, what memory can we free up? So that way you never have a variable that points to nothing. Okay, that points to like an empty spot in memory, because that memory won't get freed up till the variable is no longer used. Okay, so you have this process that's constantly checking, okay, is this variable possibly going to get used anytime further going forward? Or are there multiple variables referring to this thing in memory? And are all of them done with? And once all these variables are gone and there's nothing else referring to this thing in memory, then we'll free up the memory. Okay, that's why you generally don't have to think about these things when you're using Python, when you're using Ruby, when you're using JavaScript, pretty much any of these higher level languages that use garbage collection. And which is great. The problem is that there is a speed cost, because now you have this additional process that's constantly having to check, can I free up the memory yet? Can I free up the memory yet? Can I free up the memory yet? And when, the more things that's done for you, well, that's also just going to reduce the speed of your program. So basically, C, I manage memory myself, so I can create something really fast, because memory is only going to be touched when I want it to be touched, and no other time are we thinking about it. But I have that whole issue of like dangling pointers and things like that, where I might be referring to something that doesn't exist. In Python, JavaScript, Ruby, I have garbage collection, so I never have to worry about dangling pointers. None of those kind of memory-based runtime errors, but they're not going to be as fast because you have this garbage collector that's continuously running. Okay, so here's where we start to get into this our tug of war. Was like, how can I get the best of both worlds? How can I get memory safety, yet still maintain that speed benefit? Okay, but just to kind of show you an example in Python, so because Python works a little bit differently, and generally all the higher level languages kind of work in this way. In this case, what happens is if I say like A equals a new duck object, and then I say B equals A, well, basically what's going to happen is what you're really copying is over as a pointer under the hood. So now I have two variables referring to the same object in memory. And again, another reason why you need a garbage collector tracking all the references to that thing. Okay, and that's why it makes it hard to give memory safety at a lower speed cost, because you have to track all these multiple references and make sure you clear them up and clean them up. Okay, and there's not really a good way to kind of like check for that, to kind of make your programming better, to make that more efficient. So again, here's just another example, kind of the same as the example we did before, where I create, like, instead of a number struct, it's a number object. So we define that number. I say, hey, A equals a new instance of this number object. I do B equals A. Then we change B's num property to 6, but that's going to change both of them, because technically they're both referring to the same object. Because again, these higher level languages, it's going to pass by reference instead of making a copy like it did in C. So now that we see like the behavior in sort of like these two paradigms, and like, again, the pros of C, that finer tuned memory management, which means faster speed, but dangling pointers. And then we have Python on the other end, where you have, memory safety because you have garbage collection, but again, there comes a speed cost with that. Rust tries to kind of say, let's do it differently. Let's come up with another way that's not these two options. Like pretty much every other language generally falls into one of those two categories. Let's actually create a whole sort of new paradigm for how we can make sure that we don't have these memory issues, but we can still maintain the speed. Okay. And that brings us to the Rust programming language. Okay, it's a general purpose language, which means you can generally build anything with it. Okay, with Rust, I mean, basically you want to build web applications, and nowadays they have all sorts of great libraries on like using WebAssembly. So you can create all sorts of really cool stuff using like WebAssembly. There's like Tori, which you can use to make desktop apps using Rust, which is a new cool thing. Then there's you can make mobile apps with Rust. You can basically do anything with Rust. That's why it's a general purpose language. It's multi-paradigm, which means it has many of the features you'd expect in an object-oriented programming language. So while it doesn't have classes, you do have structs, and you are able to define functions that go with those structs. So you essentially get to the same place. And then you also have things that you would expect in like a functional programming language, like they have pattern matching. Generally one of my favorite features in any programming language that has pattern matching. I'm a big fan of that. It's actually a really cool, powerful feature. I'm excited for the day we can see pattern matching in JavaScript. They just added it to Python, but it's a really, really cool feature. So it has all those sort of features of like different paradigms of programming: procedural, functional, object-oriented programming, etc. It's type safe. So if any of you guys have programmed Rust is pretty strict on typing. So you have to make sure you define the types, and basically everything has to be really is pretty rigid in Rust. And that's why it's going to be able to give you that speed and avoid those errors in the runtime. Okay, so it's a pretty strict language. And it's memory safe. So provides you type safety, memory safety, provides you all the safety. Like that's Rust's number one goal. It's not the goal of Rust is not to be easy, it's to be safe. If you can create running software in Rust, it's going to run fast and it's going to run safely. That shouldn't have any runtime errors for the end user. And that's sort of like the promise of Rust. Okay. Although, I mean, once you kind of learn how to do things in Rust, it's really not that bad. It does give you like that level of speed as C, gives you some niceties that actually kind of make it easier to work with, because anytime you have a newer language, you get to build in all those niceties that didn't exist back in the early days of like C and C++, like you're a standard package manager and standard tooling for a lot of those things. So it gives you this really nice environment to create the nice, safe, fast software. Okay, but in Rust, the way it works is that it generally tries to enforce the idea that there can only be one reference to that thing in memory. Okay, it becomes a lot easier to know if there's a problem if I know that only one thing can be referring to that thing at any given time. Okay, so in this case, if I were to say A equals a new duck, okay, in this case it would be like a duck struct, and then I said B equals A, it would not create a copy. So we're not creating a new duck. We're not creating two references. So A and B will not refer to the same duck. What will happen is that just the reference will just move. So A will just refer to null. It just won't refer to anything. It's not pointing to that thing in memory. Okay, and then B will be pointing to the duck. That reference will have moved variables. Okay, and this makes it easier for Rust during its compile time checks to check that, hey, did you accidentally refer to something that shouldn't actually exist? Because if I go back then use that variable A after I assigned the duck to B, then the Rust compiler can tell me, it's like, hey, Alex, like the duck's not going to be there anymore. Like you passed it off. Okay, and it'll give me errors that can help me catch those errors before it compiles, before I actually have users actually use the software. Okay, and again, that's sort of like the benefit here. And if you ever use Rust, you'll notice, like, because it's so strict, those the compiler errors are really detailed, and they really kind of like point you in the very clearly in the right direction, which is probably my favorite thing about Rust. Like best errors of any compiler, hands down. Like it really just like, that's your problem, and it can give you really helpful suggestions as well. Because it's so strict, it can really identify a lot of the problem up front. But of course, when you're writing in a stricter language, you can always get frustrated because you're seeing those compiler errors more often to get to that final code. But your final code is going to be a lot better for it. Okay, so just here's like an example, so we can kind of see like, so this is straight from like the Rust documentation. So essentially, what happens here is like, first off, we define a function called eatbox i32. Okay, now a box in Rust is an object that allows you to allocate memory on the heap. So it's just kind of like that malloc function that we saw earlier in C that says, okay, hey, let me go get some memory in Rust. Basically, what this is saying is like, okay, hey, let me allocate some memory on the heap big enough to hold the object I specify. So in this case, I'm saying, hey, I want to have this function as an argument. Okay, I'll just use my little pointer here, the point where I'm looking at. This function is going to take an argument that is a box basic memory on the heap that holds a 32-bit integer. And it's just going to print it out. But the key thing here is that we're passing the actual value. Okay. You'll see that like the difference between here when we see the ampersand. Okay, so we're passing the actual value. So essentially the function is going to get a copy of it, not necessarily the original. And then here we're going to have a function called borrow I32. Okay, so this function, what it does, it's going to borrow the value, which that's what that ampersand is going to mean. So it essentially means a reference in the same way we use like with pointers in C, where it's a reference to the thing, but because you're passing it the reference, it's going to borrow the reference from whatever variable had it before. So that old variable that had it is not going to have it until this thing is done using it. Again, because that reference can only be in one place at a time. This way the compiler can always make sure at any given line, are you using the variable that actually has the reference currently? And we'll be seeing how that triggers an error in a second. And again, errors are your friend. That's the whole point. Okay, the idea is you rather get compile time errors than runtime errors. Okay, so we have these two functions. So now we get to the main function where the actual program, like what's actually going to happen. The program starts running. Okay, first thing it's going to do is creates a 32-bit integer. So see, it creates a new box, and inside of it we put the number 5. Okay, and then what we do is we create another integer. Okay, but this is on the stack. That's why it's called stack. So because we didn't declare it in a box, it's assumed to be allocated on the stack and memory. So again, we don't have to worry too much about the stack because the stack kind of cleans itself. And that's just the number 6. So now what happens here is that we run the borrow function. So we're borrowing the integer. So first we run the borrow I32 function once, and we pass it the box I32. Everything's good. So while that function is running, technically the box 32 that box I32 variable no longer has a reference to that box. It's gone. Okay, because the function is borrowing it. Okay, so essentially at this point, it's going to borrow that reference. So right now, technically, this version of box 32 would own the reference until this function is done. And then once the function is done, it then returns the reference. Okay, so this basically we run the function. Again, they're borrowing it. They're saying, hey, I'm going to be using this variable now. Nothing else can use this variable while I'm using it. And then it gives it back when it's done. Okay. And this way, again, the compiler can know, hey, if anything else tries to access that original variable in the meantime, there's a problem. Okay, because technically that function's got it right now. Okay. This allows the compiler to be able to kind of like, just make sure nothing could possibly go wrong when you run the software for you. Okay, so now here again, we have some curly brackets. Okay, so if you're familiar with like JavaScript, you can use just like a random pair of curly brackets to create like a scope, to create like a closure. Okay, so to help you be able to create variables that are only scoped within those curly brackets. So here we create another variable, and this variable is a reference to the I32. So essentially this variable is borrowing the reference. So when we say, hey, this ref to I32 equals box to I32, that technically now that's borrowing it. So this now owns the reference. And then this is right now pointing to nothing in the meantime. Until this is done borrowing it, this cannot use that reference to the thing. So what happens in the very next line? We use the eatbox function, and we try to pass it the box I32 variable. But what just happened? The line right before, it no longer has the reference anymore. It's pointing to nothing. So this is going to throw an error because what was inside this variable has been borrowed. Okay, and then Rust is going to be like, hey, you can't do that because we have a rule, only one reference at a time. And the thing is that now I can go back and like refactor my code to kind of avoid that problem. So again, it does take a little while to kind of get into that sort of Rust way of thinking, but the idea is that this sort of discipline that it enforces will just result in, again, much smoother running code, and you get all those speed benefits of sort of having that manual memory management. And generally, you probably won't have to do too much explicit memory management too. So because Rust can do it for you because of this way of expressing where things are. Okay, so theoretically, to solve the problem, we would just comment out that line. Okay, and then basically when I run this runs fine because I'm using the reference. I'm using ref to I32, which now owns, right now is borrowing ownership. Okay, and then the minute this curly bracket happens, this scope is closed. So then this variable would be destroyed. which means, hey, I'm done with the borrowing. I don't no longer need to borrow this reference anymore. And then that reference would then be returned to box I32. So box I32 now has the reference back, and then we can do that function again, do the eat box I32, pass it box I32, and it actually works this time because technically it's received ownership of that reference again. So again, the idea is you're playing like hot potato, and the only one who can use it is whoever has it. Okay. So again, when you first start programming in Rust, it does take a second to kind of appreciate that, because in other languages you just don't think about that. It's like, hey, if the variable has it, the variable has it. I'll use it whichever variable I want. But this does kind of give you like a bit of like rigor in your coding that again results in better code. Okay, and that's essentially like the big secret sauce of Rust. Like Rust has all these other great features regarding concurrency and a lot of its libraries, its tooling, but the fundamental thing that it's giving you is it's preventing, again, the hangups that you might run into in runtime errors when you're using something like a C or C++, because you could also get those speed benefits there. And I mean, those languages have been around forever, and they got lots and lots of libraries. But again, you can run into those like pointer issues and those memory reference issues, and then you get the memory safety, but without the speed costs of like using a garbage collector. So essentially, that is what makes Rust special and unique, because it's like the only language that really kind of takes that approach currently. Okay, so you're finding the best of both worlds. You get the speed, but you don't also have to hold this much headaches for us thinking about how do you allocate the memory and how do you deallocate memory. Basically, when any variable, only one thing can refer to something, and if that variable that refers to that thing gets destroyed, so does a thing in memory. And that's the beauty of it. So in that case, that whole like free function we didn't see, I don't really have to worry about that in Rust. I don't have to worry about the deallocation side of things, because there's only going to be one thing that that thing that refers to that thing, and when that variable is destroyed, that thing will be freed up. So it kind of manages itself, and yeah, makes life easier. You just have to worry about just getting the memory, using like box to allocate the memory, and then just use it. And then when you're done using it, it'll just clean itself out. So that saves you a little bit of the headache, and again, reduces the amount of errors you have when you actually run the thing. Okay. Cool. So that's, again, the fundamentals of Rust. Again, my name is Alex Merced. You can follow me on Twitter at Alex Merced Coder. Constantly putting out like YouTube videos. I think I have like probably like 1,300 YouTube videos currently on Rust, on Python, on JavaScript, on pretty much any language you can think of. At AM Data Lakehouse, that's my Twitter account for data engineering type stuff. And again, I do most of that stuff during my day job with Dremio. And then again, you can also see my blog over there at grokOverflow.com. I was actually surprised that that domain was available. But with that, that's kind of the end of the presentation. So we can take some questions now if anyone has questions about the topic. And yeah, thank you guys for having me.
Thanks very much for your talk, Alex. I think for the folks watching, what we'll do is any links or any information that is necessary, we'll include that in the email that we're going to send after the webinar is concluded. And we'll also send a copy of the video. And just a reminder again that it will be uploaded to YouTube. Just wanted to thank you very much, Alex, for your excellent talk today. It was terrific. I learned a lot. I'm sure all the people watching did as well. And we will be sending over, as I said, a copy of the video, and also for anybody watching, please feel free to check out our other virtual tech meetups coming up. I know we have 2 more scheduled for September. We have 3 for October already, and 1 for November. So we're pretty stacked up. But I think that concludes our webinar today. Thank you again, Alex, for delivering your presentation, and look forward to having you deliver a talk for us again in the future.
Would love to. Thank you very much.
Okay. Thank you all for watching. Bye-bye.